Okay, so this next section is on sampling distribution of a difference between two means. And so we kind of want to know what the shape and center and spread of the sampling distribution of x bar 1 minus x bar 2 are, and are these conditions, are there any conditions that need to be met? Well, we can kind of guess what that's going to be. Yeah, we got the shape. The population distributions are normal. The sampling distributions of x bar minus x bar is normal. In other cases, the sampling distribution of x bar minus x bar 1 minus x bar 2 will be approximately normal if the sample sizes are large enough, meaning that the sample sizes are greater than 30. Now, you do have to check both samples for normality. All right, the center, the mean of the sampling distribution is mu sub 1 minus mu sub 2, the first mean minus the second mean. That is the difference in the sample means in an unbiased estimator of the difference in the population means. And then the spread, the standard deviation of the sampling distribution of x bar 1 minus x bar 2 is, as long as the sample is more than 10% of the population, it's this. Sigma squared. So we're looking at the variance over the sample size, and variance 2 over the sample size, and then square root of that. As long as the 10% population is met. Okay. These are essentially the same conditions that we learned in Chapter 7 for doing calculations involving the sampling distribution of x bar. Now, remember that these are that we need to do both of them and not just one sample. We need to check both samples for this. Okay. All right, here we got an example. A potato chip manufacturer buys potato chips for two different suppliers, Ryder Wood Farms and Camberley, Inc. The weights of the potatoes from Ryder Farms are approximately normally distributed with a mean of 175 grams and a standard deviation of 25 grams. The weights of potatoes from Camberley are approximately normally distributed with a mean of 180 grams and a standard deviation of 30 grams. When shipments arrive at the factory, inspectors randomly select a sample of 20 potatoes from each shipment and weigh them. They are surprised when the average weight of the potatoes in the sample from Ryder Farms is higher than the average weight of the potatoes in a sample from Camberley X bar C. We're going to call that X bar C. Describe the center and shape, the center, shape, and spread of the distribution of X bar C minus X bar R. Well, the shape of the sample of the sampling distribution of X bar C minus X bar R is approximately normal since both distributions are normal. The mean of the sampling distribution is 180 minus 175. And the standard deviation, remember that this is how we find the standard deviation. The standard deviation of the first one squared, so we're looking at the variance over the number of, or the sample size of the first one, and then the standard deviation or squared, or the variance of the of X bar 2 of the Riderwood Farms. And when we work that all out, we get 8.73 grams. Interpret the standard deviation of the sampling distribution of X bar sub C and X bar sub R. Find the probability that the mean weight of the Ryder sample is larger than the mean weight of the Camberley sample. And should the inspectors have been surprised? The mean of the Ryder sample is larger than, so then X bar C minus X bar R is negative. The graph below shows the probability of this happening. And this should be shaded in here. I just can't shade it on my computer. So when I work this all out, and the probability that it's less than 0, that the difference is less than 0, is the probability that Z is less than. So we look for get our Z score, and so we want Z is less than a negative 0.57, which is 0.28. And the inspector shouldn't be surprised because the Riderwood sample will have a higher mean more than 1/4 of the time, since 0.28. All right. So, what is the standard error of X bar 1 minus X bar 2? And is this on the formula sheet? This is the formula for the standard error. It's your sample, it's the square root of your sample variance over your first sample variance over your sample size plus this sample variance over the second sample size. And is this on the formula sheet? The formula for the standard deviation of the sampling distribution of X bar minus X bar is included on the formula sheet. However, the formula for standard error is not included on the formula sheet. So just know that. What is the formula for a two-sample statistic? And is this one on the formula sheet? And what does it measure? Sample means, the difference in your sample means minus the difference in your population means over the square root of your variance squared, your first sample variance over the sample size plus the sample variance over the second sample variance over the second sample size. And is this one on the formula sheet? It's not on the formula sheet. The formula for the standard deviation of the statistic is on there, but this formula is not on there. And what does it tell us? It tells us how far the difference in the two means is from its mean in standard deviation units. And the distribution, what distribution does the two-sample statistic have? And why is this a T statistic rather than a Z statistic? And how do you calculate the degrees of freedom? There's a lot in that question right there. All right, it has approximately a T distribution. Use the T statistic when we don't know the population's standard deviation. And there are two ways to calculate the degrees of freedom. The first one is by technology, and there is a somewhat messy formula that you can use. Use the T distribution with degrees of freedom calculated from the data by a somewhat messy formula that's in your calculator, and with this option, the degrees of freedom may not be a whole number. Your other option is the conservative method, and use the t-distribution with degrees of freedom equal to the smaller of the two, either your first sample size minus 1 or your second sample size but minus 1, whichever one is smaller. And with this option, the resulting confidence interval has a margin of error as large as or larger than is needed for the desired confidence level. The significance test using this option gives a p-value greater or equal to the true p-value. What are the conditions of a two-sample t interval for mu1 minus mu2? As usual, it's normal, random, normal, and independent. And we do have to check and make sure you check for both of those. The data are for random, the data are produced by a random sample of size n1 from population 1 and random sample of size n2 for population 2, or by two groups of size n and n1 and n2 in a randomized experiment. So you have to check both of those. Both population distributions have to be normal. If the sample sizes are not greater than 30, then you need to graph and look. And independent, if both of the samples themselves and the individual observations in each group are independent, well, you need to check if they're both independent. When sampling without replacement, you need to check the 10% rule. What is the formula for a two-sample interval, t-interval, of mu1 minus mu2? Is this formula on the formula sheet? Well, there it is. Your first mean, sample mean minus your second sample mean, plus or minus your t-star, and then your standard error. Is it on the formula sheet? This specific formula is not on the formula sheet, but you are given a general formula for the confidence interval and the formula for the standard deviation of the sample distribution. So you're given the general formula, and you're given this formula for the standard deviation. So you just have to know to put them together. Okay, is it okay to use a calculator for the do step? Well, we all know the answer to that by now. It's okay to use your calculators. If you do not write the equation using the conservative degrees of freedom. These will produce the same will not produce the same answer. If you want to write out the formula, leave t-star in the formula instead of putting the conservative critical value. Then report the calculator's interval and degrees of freedom. Okay? So just make sure you do that. Okay, here we got an example. Do plastic bags from Target or plastic bags from Bashas' hold more weight? A group of AP statistics students decide to investigate by filling a random sample of 5 bags from each grocery store with the common grocery items until the bags ripped. Then they weighed the contents of the items in each bag to determine its capacity. And here are the results in grams. Okay? Conduct and interpret a 99% confidence interval for the difference in the mean capacity of plastic grocery bags from Target and Bashas'. Okay. So, you know what we got to do. State. We want to estimate U sub t minus U sub b, 99%, confidence level, where U sub T is the mean capacity of plastic bags from Target in grams, and U sub B equals the mean capacity of plastic bags from Bashas' in grams. Plan. If the conditions are met, we will calculate a two-sample T interval for U sub T minus U sub B. Okay, so we're going to check random. The student selected a random sample of bags from each store. Normal. Since these sample sizes are small, we need to graph it and check to see if the populations are normal. And I did this on the Inspire, and that's okay. You just have to be able to show it on your paper on the test. Okay? And since there's no obvious skewness or outliers, it's safe to use T procedures. Independent, the samples were selected independently, and it is reasonable to assume that there's at least 50 grocery bags in the store. All right, so here's our do. All right, when you put the data into your calculator, Target's mean was 12,825, and its sample standard deviation is 1,912.5. And the sample mean for Basham's is 9,234, and the sample standard deviation is 1,474.2. Using conservative degrees of freedom of 5 minus 1 equals 4, the critical value for 99% is T star equal 4.604. The confidence interval is this: Target's mean minus Basham's mean, plus or minus our T star, and then we've got our variance, or our standard deviation squared, which is the variance over the total, over the sample size, and the second one. And when we do, we get a confidence interval of negative, it could be anywhere from a negative 1,380 to 8,564. That's the difference in the two. If you use technology, you're going to get a degree of freedom of 7.5, and so your confidence interval would be from a negative 101 to 7,285, which is quite a bit smaller, okay, smaller range. Does your interval provide convincing evidence that there is a difference in the mean capacity between the two stores? Oh, sorry, I got to conclude. So, conclude, yes. We are 99% confident that the interval from 1,380 to 8,564 grams captures the true difference in the mean capacity of the plastic grocery bags from Target and from Basham's. Does your interval provide convincing evidence that there is a difference in the mean capacity between the two stores? Since the interval includes 0, it is plausible that there is no difference in the two means. Thus, we do not have convincing evidence that there is a difference in the mean capacity. However, if we increase the sample size, we would likely find a convincing difference, since it seems pretty clear that the Target bags have a bigger capacity. So you just need a bigger sample size. What are the conditions for conducting a two-sample t-test for the population mean minus the population mean? All right. So, you know what they are. Random, normal, and independent. And we need to check for all of those. Again, you need to check both sample sizes, both samples, to make sure that they're random and normal. If there's not more than 30, then you need to check for, if the sample size is less than 30, then you need to graph it and check. Okay, so here we go. New problem. In commercials for Bounty paper towels, the manufacturer claims that they are the quicker picker-upper, but they are also the stronger picker-upper. Two AP statistics students, Wesley and Maverick, decided to find out. They selected a random sample of 30 Bounty paper towels and a random sample of 30 generic paper towels and measured their strength when wet. To do this, they uniformly soaked each paper towel with 4 ounces of water, held 2 opposite edges of the paper towel, and counted how many quarters each paper towel could hold until ripping, alternating brands. Here are the results. Okay. Display these distributions using parallel box plots and briefly compare these distributions. Based only on the box plots, discuss whether or not you think the mean of the Bounty is significantly higher than the mean of the generic. Both distributions are roughly symmetric, but the generic brand has 2 higher outliers. And I did this, of course, on the Inspired. High outliers. The center of the Bounty distribution is much higher than the center of the generic distribution, although the range of each distribution is roughly the same. The interquartile range of the Bounty distribution is larger. Since the centers are so far apart and there is almost no overlap in the distributions, the Bounty mean is almost certain to be significantly higher than the generic mean. If the true means were really the same, it would be virtually impossible for so little overlap. Use a significant test to determine if there is a convincing evidence that the wet Bounty paper towels can hold more weight on average than the wet generic paper towels. So, state. We want to perform a test of the null hypothesis being that the mean of the Bounty minus the mean of the generic equals 0, meaning there's no difference, versus the alternative hypothesis, which is the Bounty mean minus the generic mean is greater than 0. At a 5% level of significance, where U sub B equals the mean number of quarters a wet Bounty paper towel can hold, and U of G is the mean number of quarters a wet generic paper can hold. Plan. If the conditions are met, we will conduct a 2-sample t-test for the difference in the 2 means. So, check for random. The students used a random sample of paper towels. Check for normal. Even though there are 2 outliers in the generic distribution, both distributions are reasonably symmetric, and the sample sizes are both at least 30, so it's safe to use the T procedures. Remember, if you got more than 30 or more. Check for independent. We can samples were selected independently, and it's reasonable to assume that there is at least 300 paper towels of each brand. So, do. Okay, the first thing you need to do is get your mean and standard deviation for our samples. And the mean for Bounty is 117, the standard deviation for Bounty was 6.64, and the mean for the generic is 88.1, and its standard deviation is 6.3. So, find your test statistic. Remember, it's the sample means, the difference in the sample means minus the difference in the population means. And then, of course, this is our variance squared over sample size for both the Bounty and the generic. And when we do, we get a test statistic of 17.64. Okay? P-value using either the conservative degrees of freedom, 30 minus 1 is 29, or from technology, you get the degrees of freedom to be 57.8. And anyhow, the p-value is going to be approximately 0. So conclude. Since the p-value is less than 0.05, we reject the null hypothesis. There is very convincing evidence that the wet Bounty paper towels can hold more weight on average than the wet generic paper towels. Okay. Interpret the p-value from B in the context of this question. Since the p-value is approximately 0, it is almost impossible to get a difference in the means of at least 29.5 quarters by random chance. If the two brands of paper towels can hold the same mean amount when wet. So it's almost impossible for that to happen. Okay. Using two sample T procedures wisely. Okay. When doing two sample T procedures, should we pool the data to estimate a common standard deviation? Is there any benefit? Are there any risks? Okay. Do not pool the data for T procedures. We do have to pool when doing significance tests for the difference of two proportions, but not with means. Should use two sample T procedures with paired data. Why not? And how can you know which procedure to use? Okay. Do not use these procedures with paired data because the two sample T procedures with paired data, because in paired data you aren't looking for the difference between the means of the two groups. You're looking for the mean of the differences. You determine which process to use by looking at the way the data is collected. Matched pairs experiment equals data paired. Paired data. One sample t-test. Completely randomized experiment or stratified sampling equal the difference of two means equal a two sample test. So just be careful which one you use. Okay, here's another example. Okay, suppose you are designing an experiment to determine if students perform better on tests when there are no distractions, such as a teacher talking on the phone. You have access to 2 classrooms and 30 volunteers are willing to participate in your experiment. Design an experiment so that a 2-sample t-test would be appropriate inference method. Okay, so here's an example. Okay, on 15 index cards, write A, and on 15 index cards, write B. Shuffle the cards, hand them out at random to 30 volunteers. All 30 subjects will take the same reading comprehension test. Subjects who receive card A will go to a classroom with no distractions. And subjects who receive B cards will go to a classroom that will have the proctor talking on the phone during the test. At the end of the experiment, compare the mean score of the subjects in room A and the mean score of the subjects in room B. Design an experiment so that a paired t-test would be appropriate. Inference method. Okay. Using the same procedure in part A, divide the subjects into 2 rooms and give them the same comprehension test. One room will be distraction-free, the other room will have a proctor talking on the phone. Then, after a short break, give all subjects a similar reading comprehension test, but have the distraction in the opposite room. At the end of the experiment, calculate the difference in the 2 reading comprehension scores of each subject and compare the mean difference with 0. Okay, so it's asking us which of these experimental designs is better. Deciding when it's appropriate to use a 2-sample t-test and when it's appropriate to use a paired t-test is kind of confusing sometimes. And so we need to kind of get a good idea of what's going on. In this, the experiment design in Part B is better since it eliminates an important source of variability. The reading comprehension skill of the individual subjects. In other words, if somebody is a poor reader, that's going to kind of skew our data. So that's why if we switch rooms, it eliminates that variable. The key distinction on whether to choose a 2-sample t-test or a paired t-test is this. The key distinction is how the data is produced. In an experiment, if the groups were formed using completely randomized design, then the 2-sample t-test is the right choice. However, if the subjects are paired and then split at random into two treatment groups, if each subject received both treatments, then a paired t-test is appropriate. So that's why this one's a paired t-test and this one's a 2-sample t-test. All right? And that's it.